Okay, Mr. Chun, you now may begin.
Hi, welcome to Energy Modeling 101. My name is Reynold Chun and I work in the Honolulu district. Also presenting is Mr. Keane Nishimoto, also a mechanical engineer here at the Honolulu district. Let's see, let me go over the training objectives. This is just a basic energy modeling class, as you notice by the 101 title. It's geared to a recent mechanical engineering college graduate or maybe a summer hire who had just been introduced to energy modeling. We're going to review some terminology and definitions, review the basics of energy modeling as related to the design process. We're just going to touch over some QC, quality control options regarding the energy modeling inputs, and then just touch on some LCCA, or life cycle cost analysis. The websites, well, the slides are actually kind of peppered with hyperlinks to websites, and we listed a bunch of names at the end of the presentation. So if you have any interest in self-study, and if I don't scare anybody away by the end of the presentation, feel free to go to the websites or call any of the points of contact up. Just some basic review. R value, our U factor, just remember R is U equals 1 over R. Solar heat gain coefficient is SHGC. The schedule, when something is on or off, or when the building is occupied, also refers to like a thermostat schedule. Building mass, plug or process loads, HVAC. ASHRAE 90.1, ASHRAE 189.1. Just remember that even though ASHRAE stands for American Society of Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE 90.1 and 189.1 isn't just for heating and refrigeration and air conditioning engineers. There's a bunch of prescriptive requirements for architects, for building envelope, and for electricals, for lighting. And even in 189.1, there's some issues about building siting. So it's not only for us HVAC engineers. See more terminology, and how ASHRAE 90.1 defines what needs to be in the energy model. We'll go over this in a little more detail later, so I won't read the whole slide. Okay, now why do we have to do energy modeling? Basically, we got to do it. I'm going to go ahead and list a bunch of UFCs and criteria, but we'll just agree that we all got to do it. So here's a bunch of UFCs, ESA, that's by law, EPAC by law, DoD sustainable policies, Department of Army memorandum, and a whole bunch of the ECBs. And this is not the most recent one, but this is the one that does highlight energy modeling, so 2011-1. And there are a bunch of others, but that's, if we want to go over criteria, I think that'll take up an entire hour. But we'll just agree that we got to do it. Now, there is some debate on what do we have to model to and what the target is, but that's for another webinar too. So we're intending this to be just really, really basic. Now, just to highlight some of the requirements that require energy modeling, going into the UFC 3-400-01, and this is the UFC for energy conservation. For renovations, it applies to projects where renovation costs are equal to or greater than 25%. And, we do some Navy projects, so for Navy, they use a 50% threshold. Then the entire building needs to be brought up with compliance to new code. And then for projects less than 25%, do the best you can. And then for new buildings, this is required. It shall be designed and constructed in accordance with the EPAC 2005. And for 90, in reference to 90.1, it needs to achieve at least 30% below the level achieved as prescriptively required by ASHRAE 90.1. And that goes into why we need to do an energy model. We need to compare it to a baseline. Now, for the energy compliance analysis, basically we're looking at the second to the last paragraph. Again, performance rating report is listed in ASHRAE 90.1 Appendix G. And Appendix G it gives us some protocols in terms of how to calculate the baseline and how to calculate the proposed building. Now, for the life cycle cost analysis, it is required for new construction under UFC 3400-01. And LCCA is required, and the predicted energy usage from the facility, from the energy model, is kind of what we have to get the reoccurring costs in terms of energy for the life cycle cost analysis. So energy modeling is required and is required when we do the LCCA. Okay, that's it for the terminology. Now let's go to the process. This is the basic steps, how the PDT would be using an energy modeler. The energy modeler would run the calculations based on the inputs. So that's number 1 and 2. We're going to analyze the outputs and then look at the outputs and inputs that we can get the biggest bang for the buck. We'll modify the inputs and then provide it to the energy modeler, and then repeat the process until a desired outcome is met. And again, that's like your target. Just don't go too crazy until your energy modeler to run the energy model for a solar tube, one solar tube. It takes quite a bit of effort to run an energy model. So find the bigger items that we would impact the energy model with, and then we'll run the energy model based on those modified inputs. Okay. And some of you probably heard a bunch of software, bunch of tools that we can use to do energy modeling with. Erdic Cyril did a great paper on comparing different software that's available. Some are free, some are paid for. And if you are interested in looking at the entire report, you can look at the hyperlink below. But they looked at the different software. We're currently using Trace 700 and eQUEST and also Carrier HAP. So that's the top 2, 3, and then the second to the last one. Just like I kind of grew up using Carrier HAP, so I'm kind of familiar with it. We've been doing a bunch of energy models using eQUEST recently. So yeah, those are the three ones that we're most familiar with. And in addition, you can always go to the internet or hyperlinks to get tutorials or download the free eQUEST software from the DOE website. Unfortunately, Trace 700 and Carrier HAP are paid programs, but you could always go to the website and take a look at the tutorials and see what's available, and then you can decide whether you want to pay for a subscription or not. I did inquire to headquarters whether we want an enterprise license for Trace or Carrier HAP, and headquarters is currently looking to it, but based on the size of the anticipated contract, we don't really think that we're going to be able to get an ELA for Tracer. But though eQUEST is free from charge, so you can go to that website and download the eQUEST software. Okay, so this is just a summary of the planning and design project schedule. So when are these computer simulations done? For you government folks, it kind of highlighted when each step of the process is. So DD1391 is in pre-design, schematic design, design development, code 6 or code 7, whether it's design bid build or design build. And then your final design or design complete is in your construction documents. So we're recommending that we use eQUEST maybe in the more schematic stages, and then train, trace, or carrier HAP in the more design development stages. Okay, so this just kind of highlights what we're going to be talking about next. We're going to be talking about the pre-design stage. Okay, so the DD1391 to the 35% design stage. Just remember the model is just good enough to ensure that the PDT is on track. The more granular the inputs, the more granular the model. But at 1391 to 35% design, we don't have all the detailed inputs. So we're just running an energy model just to make sure the PDT is on track to meet its energy targets. If a BIM model is available, there is technology that can quickly transfer data from the BIM model or Revit model over to the energy modeling software. There's also some Revit or BIM tools that can do energy modeling. It's just that at this time, I'm not too sure that it is quite proven yet. So I would really rely on using eQUEST or carrier HAP. Let's see, and also at this time, the PDT should consider general energy conservation measures or ECMs, such as daylighting, siting, and building massing, and even perhaps central plans and submetering. So catch the big stuff in the schematic design stage, and then we'll move on to the more granular things in the design stage. But let's take a step back and talk about the inputs to the energy model. And I know this is kind of sketchy with my little stick figure, but I don't get the point across. Let's say we have a person in a building. Let's give them some walls, a roof, and a window. And by the way, let's give them a working buddy. And okay, they need both workstations and lights. And after a while, we need to separate them. And oh, by the way, after a while, they don't like working together. So one works during the day and one works during the night. And so what does this have to do with building energy? Well, it takes energy to move energy. So for air conditioning, whatever energy we add to the building, we need to take it out. And then for heating is opposite. So for buildings with a lot of hot people, you don't need as much heating energy. But you can't size the equipment assuming you have hot people. You just use less energy. So the team will give all these inputs to the energy modeler, and kind of the general checklist of inputs, and then outputs of energy model, and then you could choose which ones you want to focus in on. But maybe the team can't pursue different things for certain reasons. Say, for example, you can't change the windows because the windows are historic, but at least we know why and how much energy it would contribute to the building. Okay, so here's the space inputs in a little more detail. And this is getting to the, I guess, the college level formula things for heat transfer. The roof, we have UA equals delta T plus the solar heat gains. The walls, kind of similar. We have conduction and also the solar heat gain to the, I'm sorry, the windows, we have solar heat gain and also conduction to the windows. And then the model will also take into account the mass of the building and the reflectivity of the building. To just define the formulas, U equals 1 over R. R is the thermal resistance. A is the surface area. Delta T is just delta T across the surfaces, the ambient temperature versus your room design temperature. The plug loads. Generally, plug loads are all sensible, but they could also be latent too. Say if you have a coffee pot, it all will give out latent heat. People give off sensible heat and also latent heat, and your lights are typically just sensible heat. And this is a slide showing the generalized calculation of the building envelope for conduction. The sum of the R is equal to the thermal resistance of the entire envelope. So just calculating, just summing up the R's across the envelope, we have R of 7.5, actually is mop per hour, MPG, moving air. The R, the vinyl siding, R of the plywood, R of the 19 batt insulation fiberglass, and if there are studs in there, we're going to have to discount the total R value using a method in ASHRAE 90.1. We have a R of the half-inch thick drywall of the interior surface, and an R of the thin still air film on the inside. So the sum of R in this case is 22.5253, assuming continuous R19 batt fiberglass continuous insulation. U equals 1 over R of 0.044. So conduction, little q equals UA delta T, and big Q equals sum of little q over time. So for you math folks, big Q is the integral of little q over time, which is typically going to be a year. And then you could also look in ASHRAE handbooks, fundamentals, which will give you a detailed calculation of what we just showed here. Roof data. Conduction is going to be similar to the wall conduction. So I didn't add up the entire assembly, but it's going to be a similar calculation. Just remember the heat flow is perpendicular to the surface. So in the case of the wall, heat flow was horizontal. In the case of the roof, heat flow is going to be vertical. It does matter if you go into the details of ASHRAE handbook, which still air film you're going to be using as, in terms of the R value. So just remember, heat flow is perpendicular to surface. Okay, remember this slide? This is the terminology slide. And just remember ASHRAE 90.1 requires certain things to be met in terms of the simulations program, the software. We just can't pick any software off of the shelf. Now, ASHRAE does its best to make the models predictive. However, models are just models. So if the actual energy does not reflect what's assumed in the model will hence not be a good predictor. And ASHRAE does state this as a caveat in its first paragraph, Appendix G. But it's the best we have, so let's go with this. So according to ASHRAE, the energy model simulation program needs to account for 8760 hours per year, which is pretty much the entire year. And it needs to take into account hourly variations in occupancy lighting power, plug loads, thermostat set points, HVAC efficiencies, and you also need a schedule defined by each day of the week and holidays. You know, I just mentioned it, but it does highlight that the energy model needs to take into account the part load performance curves for mechanical equipment. So in the case of, for example, air-cooled chiller, where it's more efficient and 100% load, we need to account for the not as efficient equipment if it's only running at 10%, 30%, 40%. So it does need to take into account part load performance curves. So let's go back to our little simplified picture. So I hope I didn't scare everybody yet, but let's apply this 90.1 to our appendix G requirements to our simple building. And now is actually not so simple. Delta T varies over time, and then at minimum we need to take into account for each hour of the year, so 8760 hours per year. E is a function of solar angle. That's kind of right below the building. So E incidence total irradiance. And it will vary by season, and it will vary from hour to hour. And if you remember your sinusoidal curve, it kind of matches your sinusoidal curve, but it does change from hour to hour. Also, we need to take into account the schedules for people, plug loads, lights, and that varies all over time. And then, let's see, the point I tried to make here is that a simulation software is required. I mean, if you go through this once by hand, great. But if we're gonna really do this for real, you're gonna need a computer simulation. But once through by hand is great, and then from then on, pick your software, whether it be eQUEST, Trine, or Carry Out. This is just a sample of the outputs from eQUEST. It goes pretty much zone by zone. And that's what's listed on the left-hand side, system and zone number. And then it lists by area square feet, it's kind of in the middle. And then design ventilation capacity, it's an outside area. More samples of output. This is the system. If you look at the bottom, it shows the zone location within the building. And this is the annual energy consumption output by eQUEST. The Keane Nishimoto did this energy model, and it actually shows you the breakout of energy use by end use versus whether it be electricity or natural gas. So if we look at the energy pie chart, the plug loads for this particular facility is about 37%. Space cooling, which is the dark blue, which is the next highest at 32%. And then the area lighting, which is the yellow, it's at 16%. So if we take a look at the lighting, if we have less energy to the lights, the yellow would also reduce, and in addition, the blue would also reduce because we're giving out less light in the occupied space. The plug loads, that's a difficult animal to attack. They're usually mission dependent. So if we just have to remember, everybody turn off or put their computers on sleep, or try to minimize the amount of plug loads. And that would have the similar effect of the energy use in the building as the lights. So less energy to the plug loads and less energy needed for cooling. This is a couple month graphs for the peak day profile. So for this facility type, showing the pie chart in a different format, but this shows it hour by hour, actually day by day. Our day by day, and within the actually, I'm sorry, it shows it hour by hour within each day of May or June. So the x-axis on the bottom is time during the day. The N is noon, the M is midnight. So you can tell that the peak load cooling is the dark blue, and it's going to peak during the day, whether you have a higher thermal load from conduction and for solar heat gain. There's also some load at night because of the plug load. So again, if the plug loads are low, then we can reduce the cooling load. Okay, let's go back to the process. So in the previous example, the biggest bang for the buck, we were looking at the plug loads and the lighting loads. Can't really change the plug loads, so we'll go ahead and look at the lighting loads. And this chart is just intended to give the PDT a general idea of whether if you're in a different climate zone, you can consider some general strategies during the planning stage. In Hawaii here, we're in climate zone 1, we're in a cooling climate, and we would consider, again, lighting, because lighting energy would contribute to the amount of cooling we would need for a particular building. Actually, let's back up to this other slide. For heating climates, we would focus more on the insulation. Conduction is a big thing. Also demand control, ventilation, or just tightening up the building. In temperate climate zones, we can consider both the cooling strategies and also heating strategies. And also there is a shoulder period for you folks in climate zones 3 through 6, that you could actually go after economizer strategies where you could turn off your heating system or your cooling system and just go with the fans. So I think there's a lot of general opportunities, but again, when we get into the design process, we're going to have to look at more granular inputs and strategies. Okay, so looking at the daylighting, lighting strategies, we could do that by doing daylighting, which will reduce the amount of artificial light to the space. In addition to the energy aspect of it, there are non-energy savings benefits to daylighting, such as reduced worker stress and higher worker productivity, and then connecting the indoors with the outdoors. But to focus on the energy, if we reduce the amount of artificial light we need in the space, again, we could affect the schedules, lighting schedules, so we could reduce the amount of energy we need to the lights, and again, consequently, the cooling system. This is a discussion about ventilation air, and this is for another webinar, but basically we need to balance the amount of input air to the building to the amount of outside exhaust air from the building. And we follow ASHRAE 62.1 for minimum ventilation exhaust requirements. And so why do we follow 62.1? It's basically because we're dictated by DOD to follow the UFCs, which dictate following ASHRAE 62.1. So basic message here is that increased ventilation equals increased energy consumption. So we're trying to reduce the amount of ventilation air either by just minimizing the amount of outside air we need to the building to balance the exhaust rate, or we could consider strategies such as demand control ventilation. But a question here actually is that if the ventilation rate is high enough for occupant comfort, do we actually reduce or increase energy? And that's for another webinar discussing ASHRAE 55 for thermal comfort, for which considers temperature, wind velocity, and humidity. But why ASHRAE 55 again? It's similar to ASHRAE 62. It's because DOD told us to follow the UFCs, and the UFCs told us to follow ASHRAE 55. Okay, so this is the end of the planning phase, and I'm going to kind of fly to the next couple phases because we're going to talk about the design phases now. So during the planning phases, actually the arrow's going to come out too good, but we definitely fixed the site plan. We determine which areas need to be conditioned and semi-conditioned. We determine the number of floors, the utility rates. Arguably, we agreed to the space usage, the lighting, and the schedules. And then we kind of discussed the building envelope, the plug loads, and the plumbing details. And that's what we're going to work on in the design phase. So in the design phase, that's code 6 or code 7 and the bid documents. We're recommending using train tracer carrier HAP. You could also use no eQUEST. But again, I grew up using carrier HAP, and carrier HAP pretty much does everything I need to do. It does the load calc, it does the equipment sizing, and it also does the energy calcs. So I'm going to need the load calc and the equipment sizing in order to complete my design, so I might as well just use carrier HAP to do the energy calcs. But that's not to say that you can't use eQUEST. You could use carrier HAP or train trace to do your equipment sizing and your load calcs, and also finish up in the energy calcs with eQUEST. Okay, so let's go back to the inputs. What we're going to do during the design phase, we're going to validate the site plan, number of floors, utility rates, the space inputs. We're going to do that before we input it into our software, if we are going to switch to software. A good idea also to double check what was agreed to in the planning stages. And then following that, we're going to use the other inputs to size the equipment and then pick our systems. Okay, so we're going to verify the R value. Just a side note here. The energy model versus load calculation. So just remember the energy model. The rules are dictated by ASHRAE 90.1 Appendix G, and the load calculations is used for equipment sizing. So the energy model, we're trying to predict annual energy use, and again, prediction is noted because the prediction is only as good as the inputs to the model. And the load calculations, we're going to be using that to determine equipment sizing, max min heating load, max min cooling load, and then to size equipment. Let's see. One note here is that the schedules of the baseline model and the proposed model need to be the same as actually in accordance with ASHRAE 90.1. It tries to be as realistic as possible, but you need to use the same schedules. If you use some energy conservation measures, such as what we discussed for lighting schedules, we can use a different schedule just to account for that energy savings. But the scary thing for me as an energy model and as an engineer, especially in design, if somebody tells me that design for flex admin, it tells me I need to design for every possible administrative use and schedule for the building. So as a taxpayer, it's actually warning, warning, warning. It means over design, because I could design for any possible configuration of this building. Now, is there a happy medium? I'm not too sure, but I think the planning folks and the engineering folks got to get together and decide on a possible repurposing the building. So maybe perhaps design for a 5-year or 10-year purpose and then redesign after that. But we just can't design for every possible use of a building. Okay, so just a little more on the differences between the energy model and a load calculation. For load calculation, we don't need the utility rates and schedules and the mechanical details and plumbing details. We're just, for load calculation, we're just looking at the maximum loads to size equipment and not oversize equipment. highlighting what we did in the planning phase, and then the check marks, which you can't really read, but they're the bottom three. We did those in the design phase. Okay. So this is just a summary of what we did in the design phase. So at design complete, we should be at step 5. And this is the output from the Ford Shafter CDC. This is from Carrier HAP. So just another look at the outputs. Another look at the outputs. And then, and this is just a blow up of the previous slides. So from here, again, just to highlight, we can take a look at the interior lighting, space coolings and fans. Those are the top 3 energy consumers of this CDC. Okay, so let's move on to the quality control check. So how do we know if the model is correct, and how should we check it? We can check the model at any of the phases: planning, concept, or intermediate, submittal, and design complete. And how do we check it? So we could run a duplicate model and see if we come out with the same answer. We could possibly check the inputs with the plans and specs. We can check the energy model with the construction submittal and the as-built. We can check the model with meter readings. But again, does the actual schedule match the model schedule? And each has its pros and cons. And we do need to do another webinar on this because we only have this one slide. But just to highlight, do the schedules and plug load match the building usage and actual building loads? So when you drive your car, does your car actually match the miles per gallon that's published on the window? Again, you only can predict what you can predict. So check the plans to the energy model or a duplicate energy model. These are going to take some time and it's going to be expensive, but we can do it. We can challenge the inputs and assumptions. We could check the shop drawings and submittals, and that will definitely close the cycle from design to construction. And then we could run it again versus 90.1 appendix G. And we just all these suggestions are going to take time, and that's why I showed it to be expensive on there. And if we do check the model, when do we do it? Again, we do want to ensure that the PDT has an accurate model. Again, the earlier the better, but just remember at the pre-design and model concept stages, the inputs aren't going to be as granular as at the intermediate model and the design complete model. But if we do the checks earlier, we then can ensure that the model is accurate, and if there are suggestions, we could actually impact the design. So if overhead can afford it, we should do a variety of spot checks and do a variety of checks on various projects at different stages of the process. Okay, let's talk about the LCCA a little bit. This shows the cost of energy of, again, this is the CDC for chapter. Cost per year for the proposed design, and that's in the center of the center column, where the energy use is about $24,000 a year. And this would be used in doing your life cycle cost analysis calculation in terms of recurring energy costs. But again, remember the schedule is it's just based on a predictive proposed schedule. So we just hope that we're as accurate as we can get when we do the design. And it is an approximation not only of the schedule, but of course the occupancy, the plug loads, and how the building is being used. This chart is the report card that's being proposed by headquarters and will be delivered by USACE to INCOM at the delivery of the facility at the end of each project. And it does identify sustainability features, including the outputs of the energy model. So this is a summary of the scorecard of the unique energy and sustainability features. The energy use intensity, this is BTU per square foot, BTU out of the energy model. It's going to be divided by the square foot of the facility to determine the EUI. And then performance dashboard. Again, you're going to have to do your energy models in order to complete this table. And the predicted annual production KBTU. Your lead dashboard. Okay, just a summary. So we're almost done here. So just going, this is the overview of the process. The energy model, anybody can do it. If you need help, give me a call or give anybody a call at the end of these slides. There's some contacts for the Honolulu district, but I'm sure other people in other districts have done energy models. And we have done everything in Carrier Hub, and then now we can use train, trace, and eQUEST. So feel free to give us a call. Just remember garbage in, garbage out. So GIGO, and but so please make the building work, and then ask the energy modeler to run the building. The energy modeler can't fix a bad building, but a good building sure can make an energy model look good. So. Make sure the building works. We have some tools, but we don't have magic in the hat. So we can tweak a building and make some suggestions, but make sure the building works. Okay, so just a summary. This is the last slide. Okay, we did address who the audience is, and I hope you guys didn't get too bored, especially with the terminology and definitions. We did review some basics of energy modeling, review the design process, we provided some QC options, LCCA, remember all the limitations that we talked about, and I hope we provided a sufficient list of resources. If you want more, certainly give us a call. And that's it. Those are the points of contact that I mentioned. That concludes the presentation. So I could take any questions if anybody has them.
Okay, Mr. Chun, at this time I have a few questions.
Sure.
Okay, firstly I'd like to ask, at what point should the building size not be done by hand?
The building energy
Like at what point in the process? Yes.
Oh, I would recommend that you just start out with a computer model. I suggested that because when I first started in the industry, the best thing for me to do was do one practice run by hand, just so I knew what the inputs were and how to interpret the outputs. So if we're gonna do this, if you're gonna do an energy model for real, I would definitely do pick a program, pick eQuEST. It's free. If you have app, use it. If you have train trace, use it. But definitely, if you're gonna do an energy model for real, use a computer program.
Okay. And then for a second question, you reviewed several different softwares, and we would like to learn what software feeds into what software.
Oh, actually, I was relying on the serial report. We're actually using it's that serial report that they did. Slide on slide 12. Thank you. Yeah. So this is a report that Cyril did in November 2011, and they took a look at different functionalities of different softwares, and they did a pretty thorough job here. We're just familiar with carrier HAP, train trace, and eQuEST. Well, I did look at Energy Plus a little bit, but the three main tools that we have here are trace, eQuEST, and carrier HAP.
Okay. And then at what point during the design planning process should an energy model begin?
Oh, I think at, as early as you can. Once you have inputs in the model, um, and sufficient inputs, we could run an energy model. Again, it is iterative, so uh, the as the inputs change, the model should be updated. It just does take a long time to input all the inputs and then analyze it and then redo it. So don't get too crazy and say, okay, I'm going to add one little solar tube and rerun the energy model. But as soon as we have inputs to a building, we could do an energy model. I think what we're trying to do for the COS facility types, the standardization facility types, is that they have a footprint, they have a floor plan, and being instructed to run energy models for climate zones, for the worst orientation, and then we could come up with a number that the team then has an idea to look at, and if we change, for example, the R value of the wall, we can then know how would it impact the building. It's just that we just can't calculate an energy model for an ambiguous, undefined floor plan. So I think the floor plan needs to be developed point where we can put in.
Okay, Lindsay, you have a question?
I do. I was going to ask, do you know of any upcoming software that would help you deal with probable or improbable behavior of occupant users and opening windows, opening doors? Because I think one of the big pushbacks or conundrums we have is, do you design a building to be completely closed so that you can have a predictable environment and then try to design off of that? Or do you try to account for natural ventilation knowing that there's going to be some user error? And then how, if there's user error, how would you then prove that you're getting these efficiencies that your design said you would?
Sure. And I really think that we could go into a bunch of detail regarding this. And this goes back to the ASHRAE 62.1 discussion, the ASHRAE 55 discussion, and I love to explore this more in future webinars. The point you make is great, and I think the bottom line that the ASHRAE 90.1 has for scheduling is that you have to use the same schedule for your proposed and for the baseline building. So if you assume that you're going to go into economizer mode for this period of the year, and people are going to open up the windows, you're going to have to use that same schedule in both your proposed and your baseline model. Whether or not you get benefit in one way or the other, I'm not too sure. In terms of people opening, closing doors, we just have to assume that the doors are closed. You can account for a certain infiltration rate. In carrier HAP, there's a infiltration rate you could add either by CFM or by airflow or by CFM per square foot. So one absolute airflow or one absolute, not relative airflow based on square footage of the building. In my opinion, I think a strategy to promote energy efficiency is to allow users to open up the windows and then maybe perhaps sub-meter, or encourage people to actually not rely on the air conditioning system and turn it off on their own, and give the people the ability to save energy on their own rather than fix windows shut. I think, and it's similar to people turning their own lights off, turning their own plug loads off. I think once we fix the building, it's going to be that schedule forever, and we're not going to have any opportunity for people to conserve energy on their own. I think it's like driving your own car. You can personally drive it inefficiently, and it could make it worse if you allow people to control their own control their own way of working the building. I think that one of the problems we had in trying to go with natural ventilation was actually the user and the sponsor buy-in. And I think I kind of talked offline with Annette Stump when we were discussing the natural ventilation strategies for the Fort Shafter CDC. We actually did want to go with natural ventilation for their gym area, but we got a lot of pushback from the users and from the sponsors of the project, saying either there's going to be bugs in there, or the kids want positive control over their environment, or whatever the reason was. But I think it's a great option. I think we should definitely explore ways where we could give the opportunity to the users and the occupants to change their behavior to contribute to saving energy. So I know that was a long answer, but I think it goes into a non-engineering discussion.
I definitely think that answers my question. Thanks, Reynold.
At this time, if we have no more questions, I would like to thank Mr. Chun and close out this webinar. Please be reminded that it will be posted on our website, and the recording will be there as early as tomorrow. Thank you.
Thank you.